All right, let's do problem number 57 on page 270 in chapter 11. And here's the problem in the book. Right here. It says an archer puts a 0.3 kilogram arrow to the bow string. An average force of 201 newtons is exerted to draw the string back 1.3 meters. Assuming that all the energy goes into the arrow, with what speed does the arrow leave the bow? If the arrow is shot straight up, how high does it rise? Okay, so let's do the given, the find, the solve, etc. Okay, so given, you got this bow, and it's being fired straight up. So here's our arrow. Here's somebody's heart way up here, because it's Valentine's Day when we're doing this problem. All right. So what did we applied a force of 201 newtons, and we pulled the arrow back a delta x of what was it, 1.3 meters? And then we fired it and it went straight up. So what do we want to find? We want to find what velocity does it have when it leaves the bow? Excuse me. Pay attention. And for part B, those Abdu over there screwing around with JD. Yeah, you guys are in the video now. Oh, and then this part we want to know how high is it going to go, like the maximum height when it strikes the heart. All right, so let's. What's that?
You forgot the mass of the
Oh, and we know what the mass is. Yeah, we need to know what the mass is. 0.30 kilograms. So for part A, well, the work done on the arrow is going to get turned into kinetic energy. Now, I suppose when you fire it, it does lift up a little bit, but we're going to ignore that. We're just going to kind of make some simplifying assumptions that the work done when you fire the arrow results in a change in the arrow's kinetic energy. And this is the work energy theorem. So the work done when you fire it, this is force times delta x, and this is equal to 1/2 mv squared. So, this is 201 newtons, and delta x is 1.3 meters, and that's going to be equal to, well, let's just do the arithmetic. Sometimes I wait until the end to plug in numbers, but I think you'll see why in a second. So that's 261.3 joules of work. So the bow, well, somebody, when they pulled that bow back, they did 261.3 joules of work. And then when you fire it, that work, then the bow does work on the arrow and gives all that energy to the arrow. And, delta K, this is K final minus K initial, right? Anytime you have a delta. But the K initial, well, the arrow initially wasn't moving. So it had no kinetic energy. So its final kinetic energy is equal to 1/2 the mass of the arrow times its speed squared. So now I can solve for V. V equals 2 times 261.3 joules divided by the mass, which is 0.3 kilograms. And then to get V, I need to take the square root of all of that. And when I do, let's see, times 2 divided by 0.3. It was 0.3, wasn't it? Yeah. And then I gotta take the square root. And you get 41.7 meters per second. Or you could round it to 42, probably be better. And then for part B, well, look, the initial energy contained by the arrow is equal to the final energy. The only forces doing work here, once the arrow is fired, is the force of gravity. And when the force of gravity does work on the arrow, it's slowing it down. It's taking its kinetic energy away and making it gravitational potential energy. So we can say that E initial equals E final. And this is 1/2 mv squared equals, that's the energy it has right after it's fired. And it's going to go all the way up to the very top. And when it gets to the top, it's going to stop. And it's going to have gravitational potential energy. Let me zoom out a little bit. So the final energy is going to be mgh. That's my potential energy equation. Well, I don't need the mass of the arrow for this. And then I can solve for h. H equals v squared over, and I put 1/2 here, and I divide by g. And then b is 41.7 meters per second. We're going to square that. Divide by 2, divide by 9.8 meters per second squared. And when you plug those in, so I'm going to square that, and then equals divide by 2 equals divide by 9.8. And I get 88.9. Or I'll just say 89 meters. So it's going to go pretty far up there. It's going pretty fast, but you would expect an arrow. Now this, of course, is neglecting air resistance. It's in reality, it probably not quite reached that high because of wind resistance slowing it down a little bit. Okay. What's the big idea here? Hey, you listen, even though you got a 6. The big idea is this. When you have work done on a bow, all that work, you're transferring energy from some archer's arm into the elastic potential energy of the bow. You fire the bow. Now the bow does work. It does positive work on the arrow. You lose elastic potential energy, but you gain kinetic energy. Then it leaves the arrow. It's going straight up. So gravity is slowing it down, which means it's losing kinetic energy, but just as it's losing kinetic energy, it's gaining gravitational potential energy. So remember this. The work done by the net force equals a change in kinetic energy. And then also, if and only if the only forces doing work are conservative forces, like a bow or gravity, springs, then you can say that the initial mechanical energy equals the final mechanical energy. And remember the definition of mechanical energy. The definition of mechanical energy is the kinetic energy of the object plus gravitational potential energy plus elastic potential energy. And usually 1 or 2 of these will be 0 at any given point, but I don't know, they don't have to be. Any questions? That is all. Excellent.